Hey guys, Dr. Cadell, and this is the Unknown Hydrate Lab. So first, we're going to talk about what a hydrate is. So if we look at this formula right here, this is the formula for one specific hydrate. The name of this specific one is cobalt-2 nitrate hexahydrate. But it's really a unique formula because you don't see any other formulas that have this little dot in the middle and then H2O at the end with a number in front of it. So that's one way when you look at a formula you can tell that it's a hydrate. The formula actually has some relation to the actual structure. Now, if we could actually see the atoms and the molecules in a hydrate, there's a lot of order, there's a lot of structure down there at the atomic level. It ends up that in a hydrate, the first part of it is an ionic compound. That means it has a cation, something with a positive charge, that in this case the cobalt, and an anion, something with a negative charge, in this case the nitrate. And because opposite charges try to get as close to each other as they can, while like charges try to get as far away from each other as they can, that fact right there is what causes the structure in the ionic compound portion of the hydrate. So it looks something like this. The little red spheres are supposed to be the cations, blue spheres are supposed to be the anions, and so what they do is if you look at this cation right here, the positive 2 charge, this anion, this one, and this one, and this is just a 2-dimensional slice, but in 3 dimensions there'd be some out here and some in the back of the board, but they're all trying to get close to a cation. And the cations, though, they're trying to get as far from each other as they can, and the anions are trying to get as far from each other as they can. And that's what causes the structure at the atomic level in these compounds. Now in a hydrate, we also have water molecules. Now a couple things. Just because there's water there does not mean it's a liquid. These are solids you're going to see. I'm going to see an example of a hydrate in just a few minutes. It's a solid, but what the water means is that in this structure right here, so when these cations and anions make this structure, they leave a lot of space. It's kind of like if you've ever seen a painter's scaffolding with the metal bars and all that space in between. Well, the bars would be kind of like the bonds between the cations and the anions, and all that space in between, that's where the water molecules go. And they just kind of bang around inside of there. One important thing about that for us in this experiment is that the strength with which the cations and the anions are held together is really, really strong compared to how strongly the water molecules are held inside these boxes. The water molecules they're in there very loosely. It's really easy to get rid of them. We're going to take advantage of that when we do the experiment. So our goal in this experiment is to determine what an unknown hydrate is. There's basically 2 parts to that. If we can figure out the identity of this first part, the ionic compound, that's one part of it. The other part is the number right here, because different hydrates have different numbers of waters associated with them. So if we can figure out what that number is and what the identity of this is, we know what our unknown hydrate is. So let's talk about the water part first. So what we're going to do is we're going to weigh out some of the unknown hydrate. And because those water molecules are held so loosely in these boxes, if we heat that hydrate up, that's one of the properties of hydrates. When you heat them up, the water molecules leave. And that's what I'm trying to show here with this little equation up here. This says that this is the hydrate. Now this is all one thing. That bullet means that everything's stuck together, kind of like this picture right here. This triangle just means that you heat it up. So whenever you heat up a hydrate, what happens is the water molecules leave. They come out of this, right? They go off and they become a gas in the air. And so we have on this side is what we call the anhydrous salt. Now this is just the ionic compound portion of the hydrate without the waters. This plus sign means that now these are separate from each other. And because we had 6 water molecules here, we have 6 here, but different numbers for different compounds. And they're separate, and they actually go off up into the atmosphere and they're gone. So what we're going to do is we're going to weigh our hydrate, know how much it weighs, then we're going to heat it up a couple times, drive off all of the water, and then weigh it again. So the difference between the mass with the water and the mass without the water is how much the water weighs. And it ends up, if you know how much the water weighs, you can figure out this number right here. Now I take you through that in the calculations. We're not going to worry about that right now. So that's the first part, how do we get that number? The second part, the identity of this. Well, we make it kind of easy for this lab because we narrow it down to only 4. There's only 4 possibilities, guys. The ionic compound, the anhydrous salt, has to be either one of these 4, either strontium chloride, potassium carbonate, magnesium sulfate, and zinc sulfate. So guys, the way we're going to figure out which one you have is we're going to start out with what's called a flame test, which I'm going to demonstrate for you in a few minutes. But it ends up that if you take something that has strontium atoms in it and you stick it in a flame, you see this bright, vivid, beautiful red flame. It's really obvious. As a matter of fact, when they make fireworks and they want the red color, that's what they use. They use strontium atoms. Probably strontium chloride or something. So if we see a red flame, we know that we have strontium in our anhydrous salt, and that must be strontium chloride. Well, if we don't see a red flame, if there's potassium carbonate in there, it ends up that potassium atoms, when you put them in a flame, they give this kind of light purple or lavender flame. And if you see that color, which I'm going to demonstrate for you, then you'll know that you have your anhydrous salt as potassium carbonate. Well, okay, so let's say we don't see red, we don't see purple. Well, we ran out of colors, okay, but we still have 2 other possibilities. So, if we do the flame test and we don't get a red flame and we don't get a purple flame, that's still useful information because we've eliminated 2 of the possibilities and we've narrowed it down to these 2. So what we do at that point, if we didn't get a red or a purple flame, something called a magnesium strip test, which I'll demonstrate for you. And basically the idea is you take some of your unknown, put it into some deionized water, and drop a little piece of magnesium metal in there. Now it ends up, if you have zinc sulfate, the magnesium atoms in that piece of magnesium metal will replace this zinc, and you end up seeing a dark coating on that piece of magnesium, which is just the zinc atoms themselves. Now, and if you see that dark coating, you know that your anhydrous salt was zinc sulfate. Well, what if you don't see the dark coating? Well, we've eliminated everything else, no color, no dark coating, and it has to be magnesium sulfate. So that's what we're going to do. Let's go get started. All right, guys, so the first part here, what we're going to do is weigh out our unknown hydrate. To do that, we're going to start with an empty crucible and crucible cover, weigh them together, and we're not tearing anything because we want to know how much this weighs. So we're going to make sure the balance says 0 before we put it on there. It does. Pop them both in there. Close the door. Record that number. That's A1. 3 places past the decimal, little g for grams. Now we're going to take our unknown and weigh out about 4 grams. Doesn't have to be exact. Now we're going to weigh that into the empty crucible. Now we already know how much the crucible and the cover weigh, so we're going to put the empty crucible on there. Tear the balance. Okay, so now it says 0 with the crucible on there. I'm going to take my unknown, take my unknown number off, take it in my data table, take the crucible out because we never pour anything directly on the balance, and force them in, keep going back and forth until I get about 4 grams. Right there. So write that number down. That's the mass of hydrate before heating. That's my A2. Now what we're going to do is we're going to start heating it up. Remember, what our goal in heating it up is to drive those water molecules out of those empty spaces in the crystal lattice. So what we do is we take this, put it on a hot plate. I have this hot plate turned on about halfway. It's for gentle heating. So what we're going to do is put this on, take the lid, and we're going to crack it just a little bit. Leave a little opening right there. Okay, so a couple things. It's on gentle heating now because with some of these hydrates, when you first start heating them up, as the water molecules start to leave, they leave really rapidly and they start bumping and shooting stuff out of the top of that. And we want to avoid that because we need to know how much everything weighs. That's also, by the way, the reason that we have this lid. If that does start happening, they'll hit the inside of that lid, stick to it, and because we weighed that lid with the empty crucible, we're going to weigh them all together at the end. We will include the mass of anything that did get stuck to the inside of the lid. The reason we have it cracked is that as those water molecules start leaving, they need some place to go. If we just leave it closed, what will happen is the steam will come up, and it is steam, and hit the inside of the lid, condense and drip back down, and it'll never get dry pretty much. So now we're gonna wait for this for 5 minutes to make sure that all the crackling, if it's gonna happen, has stopped. After that 5 minutes, we're gonna turn it up all the way. We're gonna turn this knob on the hot plate all the way up. We're gonna heat it for 15 more minutes, okay? Then we're gonna take it off and weigh it. All right, guys, so while we're waiting for our hydrate to heat up and to drive all the water molecules away, we're going to do the flame test, and if we have to, the magnesium strip test. So what I'm going to do, though, is I'm going to show you what all the unknowns would look like, so you get a chance to see. In your data, you're going to get one of these. You're going to see a picture of one of these. So first thing, though, is we're going to use a Bunsen burner to do the flame test, and we haven't used that yet in this class, so I need to explain how to use it and how it works. So Bunsen burner, it's like this, comes with a hose, attaches to a gas outlet here, and a Bunsen burner basically has 3 controls. The first control is the handle to the Bunsen burner. It's either on or off, and that's it. If this handle is perpendicular to this nozzle, either way, it's off. If this handle is parallel to this nozzle, it's on. That's it. We don't try to control the flow with that. That's the first control. The next control is on the bottom of the Bunsen burner. There's this little knurled handle. This is a needle valve. And what this does is this controls how much of the fuel gets to the flame. The only thing we have to be careful about with this is for using this, and we back this out too far, it will come all the way out. And the problem is that if the flame is lit and you're adjusting this and it comes out, now flames are shooting out and you can burn your hand. So to avoid that, we're going to start with that needle valve all the way in, and all the way in means there's no fuel getting to the flame, so it won't start. And we're going to back it out about 1 turn. So back it out about 1 turn, and we'll adjust it from there. That's our starting point. The third control on the Bunsen burner controls how much air, and that means how much oxygen gets to the flame. So that gap right there, that controls how much oxygen gets to the flame. The bigger it is, the more oxygen there is to the flame. Now, we don't want too much oxygen getting to the flame because it blows itself out. So what we're going to do is we're going to start with that gap, about 1 millimeter or so between the top of the threads and the top of the gap, right about there. And we'll adjust it from there. So we have everything adjusted to our starting point. We're ready to light the flame. So we've got everything set. Turn on the gas. We can use a lighter, matches. I'm using a striker. And there we go. Now, I can tell I need to adjust that flame. To me, that has too much fuel, maybe not enough oxygen. So the first thing I'm going to do is reduce the amount of fuel that's getting to the flame. And that's that knurled handle, the needle valve on the bottom of the Bunsen burner. It's hot up here, but it's not going to be hot down here. So I'm going to turn this in and get that flame right there. And that's a pretty good flame. I'm going to give it a little more oxygen because I don't know if you can see it, but there's this bright blue inner cone. That's what we're looking for. That's the kind of flame that we want to get on a Bunsen burner. And by the way, the hottest part of this flame, which is usually where we want to put stuff on a Bunsen burner, is the very tip of that inner cone right there. Not up here, right there. All right, so now that we've got our Bunsen burner set, we can do the flame test. What we're going to do is we use a wood splint. It's just a coffee stirrer. Get it wet, and that helps the hydrate to stick to it a little better. Get some of your unknown on the tip and stick it in the flame. So that red right there, that tells us that we have strontium atoms in there, which means that our anhydrous salt is strontium chloride. Next one. See that lavender purplish color? That tells us that we have potassium atoms in there, and so our anhydrous salt is potassium carbonate. Now, if we get neither one of those colors, then that tells us that we don't have strontium chloride, we don't have potassium carbonate, so we're lucky enough to be able to do the magnesium strip test, which we'll do right now. But we're finished with this flame, so we're just going to turn it off and set it aside. So, lucky enough to be able to do the magnesium strip test, what we're going to do is we're going to take a little bit of our unknown, take a small test tube. Now we don't need that much. I mean, just a little bit is fine. I mean, it's probably even hard to see. Just a little bit on there, and that's actually more than enough right there. So once we put our unknown into the test tube, take some deionized water and fill it up, I don't know, about that much. Give it a few flicks, help it start to dissolve. Doesn't matter if it all dissolves or not. And then we're going to take a piece of magnesium. And we don't need much, just one piece. They look like this. And the important thing to see is how shiny they are. So I'm going to take one piece. Oh, which one is it? Drop it in. And usually it floats on the top, so we want to flick it to make sure it sinks. And then we're going to let it sit a few minutes, and we'll come back and look at that, and you'll see what happens if you have zinc sulfate. Remember, if you have zinc sulfate, you're going to get a black coating on what was a shiny piece of magnesium metal. Actually, you can probably see it starting to form already. Now I'll show you what it looks like if you don't have zinc sulfate and you have magnesium, because that would mean you have magnesium sulfate. So we take our unknown, put about, a little bit in the test tube. Again, that's more than enough. It's wet in there already. Add a little bit of DI water. Give it a little flick, help it dissolve. And put the piece of magnesium in. So this, so if it's magnesium sulfate, then you will see some small amount of bubbles. That's just the magnesium reacting with the water, but it will not get dark like it did before. So that's what it would look like if you had magnesium sulfate, no dark coating on the piece of magnesium metal that you put in there. All right, guys, so now your unknown hydrate has been heating up for a total of 20 minutes, 5 gentle and 15 strong. So we're ready to take the next measurement, which is going to be our A3. That's really hot, so we can't just touch with our hands, unless we're Matt, but nobody's Matt but Matt. So we're going to take these crucible tongs, put the lid on the crucible, turn them over, use this opening right here that's made just for a crucible. Pick up the crucible, set it on this piece of wire gauze. We don't want to set it right on the countertop because sometimes that's kind of cool and that's really hot and it'll crack the crucible. So now we're going to just let that sit and become cool enough so that we can touch it without hurting ourselves. Then we're going to weigh it. All right, guys, so now that the crucible and cover with the hydrate, the anhydrous salt in it, are cool enough to touch, we're going to go weigh it. We want to know how much everything weighs together. The lid, the crucible, and the hydrate in there, anhydrous salt. So we're going to make sure the balance says 0. And then put it all in there. Close the door, get that number 3 past the decimal. That is our A3, mass of the crucible and cover after first heating. Once we finish that, You just put it right back on the hot plate. It's still turned up full blast. And we're going to go 10 more minutes, then do the same thing. Take it off, let it cool, heat it, weigh it, and that will be our A4. Now, what we do is we take A3 minus A4. Just do it in your heads or on a calculator. If the difference is 0.01 or smaller, that means it's dry, you can stop, you're done. If it's bigger than 0.01, then you're just going to repeat this one more time. Heat it up for 10 minutes, cool it, weigh it, and that'll be A5. Not everybody's going to have an A5. Everything's done, the experiment is finished, you're good to go.